Hi there, I'm going to do a video on deriving the SUVAT equations. Those are the equations which govern motion, which you'll probably use in your physics and math class. And there's just a few prerequisites which I'm going to assume you know for this video, just so I can go through it reasonably quickly. So I need you to know what a derivative is and a second derivative. Then there's a couple of basic integrals: the integral of x with respect to x, the integral of some constant with respect to x, and then I need to know that you to know that integration and differentiation are inverse operations. As long as you know them, we can get started. So you may not call it SUVAT equations in America. Actually, I'm not sure, but in the UK we call it SUVAT because each of the letters corresponds to the quantities which are relevant. So we have S as the displacement, that's like the distance moved by, let's say, like a particle. U is the initial velocity. V is the final velocity, or it's often the velocity at time t. A, fairly obviously, is the acceleration, which is also the derivative of the velocity with respect to time, or the second derivative of displacement with respect to time, as we'll come on to. And t is the time taken. Okay, so I'll write down the SUVAT equations. Hopefully you'll be familiar with them, but even if you're not, then you can get to see how they're derived, and that'll help build some intuition behind them. So here goes. So v squared equals u squared plus 2as. S equals ut plus a half at squared. S equals vt, minus a half at squared. V equals u plus at, and finally S equals u plus v over 2 times t. Okay, great. So there's 5 equations here, but basically we only need to derive 2 of them, and then we can rearrange. We can like solve them simultaneously by substituting for a given variable, and the other 2 will come out. So the condition for SUVAT to apply is simply that the acceleration is constant. So as I mentioned before, condition for SUVAT. So the condition is that the second derivative of the displacement with respect to time is equal to some constant k. Well, k is normally a constant, but in this case, as we've defined it, we're going to have this constant as a. So let's say equals a there. Okay, so this is the only condition, and from this we're going to actually derive all of these equations. Okay, so I'll get a fresh piece of paper. So we're going to start with this. We have the second derivative of displacement with respect to time is equal to a. And then we can rewrite this as the derivative with respect to time of ds by dt. And now we can integrate both sides with respect to t, given that a is a constant. So we can say that the integral of the derivative with respect to time of ds by dt with respect to t is equal to the integral of a with respect to t. And using the fact that the derivative and the integral are inverse operations, we can then conclude that ds by dt is equal to, and then we know how to do this side, integrating a constant with respect to time. It's just going to be at plus some constant c. So c is a constant. And then again, if we refer back to our initial definitions, we can say that the initial velocity is u. So that means where time is 0, the velocity is u. So using those conditions here, at t equals 0, ds by dt, the derivative of displacement with respect to time, well, that's the velocity. So ds by dt equals u. And so substituting these in, we can say that u is equal to, well, a times t is a times 0 in this case, which is just 0, plus c. So u equals c. And so we have ds by dt equals at plus u. And this is the velocity at time t, which according to our initial definitions, we're calling that v. So I'll just go up here, and we've derived one of them successfully. So this is v, and I'll just swap these around to keep it in the form that I wrote it in initially. We can say that v is u plus at. Okay, so cool, we've derived one of them, but actually that should be quite intuitive. I've got a little graph here to show why this should be quite intuitive, a velocity time graph. So I'll label a couple of things on. So at time t is 0, this initial velocity is u, okay, and the gradient is a constant, and you should know that the gradient is given by dv by dt, the change in y with over the change in x, and this is a constant, which is exactly the condition we had before, because this is the same as the second derivative of displacement with respect to time is equal to a constant, which is a condition we started with. So this kind of makes sense that we've got like a straight line going on here, and this has come out. So okay, this is kind of, I wouldn't say obvious, but it's logical so far. Right? We have a lot of intuition behind this. But okay, we could have gone about it in a different way. So, well, not so much a different way, I guess. There's another way we could look at it. So, if you recall, we have ds by dt equals at plus u, and we could integrate this again with respect to time, right? Because on the right hand side we've got a function of time, and on the left we just ds by dt. So again, we can integrate ds by dt with respect to time, and this is just going to be equal to the integral of at plus u with respect to time. Okay, so again, same logic as before. This is just going to be s, because inverse operations, is equal to, okay, the integral of t is a half t squared, and then we multiply by the constant, so that's going to be a half a t squared, plus, this is a constant, okay, so this is going to be plus ut, plus, again, some constant of integration. And again, we can use our initial conditions to say at t is 0, s is 0, because s is the change in displacement, right? So initially it's not moved, so we can say that at t equals 0, s equals 0. So putting these into, substituting these into the equation, we can say that s is 0 equals t is 0, so this is going to be 0 plus this is going to be 0, so this is just 0 equals c. And so we can say that s is equal to, I'll swap these around just so it looks the same as we were after again, ut plus a half at squared, which if we look back at the initial sheet that we had, we can see that that's exactly the same. Yeah, we've got the equations right here. So we've now got equation 4 and equation 2, and using those two and swapping the variables around, substituting the variables into each other, we can actually generate the rest of the equations, which I won't do now because I'm running out of time, but maybe you should try that in your own time, and hopefully you'll get the right answer. Thanks for watching. I hope that was useful.